Hey everyone, and welcome to this explainer. Today, I'm going to be stepping into the dual role of your chemistry professor and your English immersion coach. We've really got two main goals here. First, to equip you with the fundamental mathematical tools you absolutely need for science. And second, to help you completely master the academic English vocabulary required to actually use them in the lab. So, let's open up this toolkit and jump right into the universal language of chemistry. Okay, here's our quick roadmap for today. We'll start with Tool 1, the compass, accuracy versus precision. Then, Tool 2, the pen, the language of uncertainty. Next up is Tool 3, the rules, significant figures. After that, Tool 4, the map, dimensional analysis. And we'll wrap it all up with Tool 5, the dictionary, our critical vocabulary box. Let's start right in with Tool number 1, the compass, accuracy versus precision. Now, we really need to nail down the difference between two English words that get mixed up all the time in science. To keep it simple, think of taking a measurement like throwing a dart. We're essentially looking at two distinct things here: where our darts land relative to the bullseye and where they land relative to each other. It's a really brilliant way to visualize the difference between just being right and being consistent. In the scientific English world, when we say accuracy, we're really talking about closeness to the target. Did you hit the true accepted value? Precision, on the flip side, is all about the reproducibility of results. If you run the experiment over and over, do you get the exact same answer? Simply put, accuracy is correctness and precision is consistency. Let's look at how this plays out in real life. Check out this archer, Archer X. They threw a super tight group of darts right down there in the bottom right corner. They are incredibly consistent, which means they have fantastic precision. But they completely missed the center bullseye, so their accuracy? Pretty terrible. And honestly, this happens in the lab all the time. Imagine you're using a highly sensitive electronic balance, but it wasn't calibrated correctly. It's going to give you a highly precise, tightly grouped mass reading every single time, but that reading will be consistently wrong. It's precise, but totally inaccurate. Moving right along to Tool 2, the pen, the language of uncertainty. So we have to talk about a pretty fundamental reality of science. Every single measuring device in existence has limitations, period. Have you ever stared at the liquid in a graduated cylinder? You read the bottom of the curve, the meniscus. Now, we can perfectly read the certain digits right off the painted lines. Here, it's clearly past the 21 milliliter mark. But where is it exactly between 21 and 22? Well, we kind of have to mentally chop up that empty space and guess the final digit. Maybe it looks like 21.6 milliliters. That 0.6, that's our best estimate. Because of that estimation, the crucial takeaway here is that absolutely all measurements contain some level of doubt. Yes, even those fancy digital scales have internal estimation. In English, we explicitly call this final estimated number the uncertain digit. It's a really critical piece of vocabulary because it tells anyone reading your data exactly where the physical limits of your equipment are. To neatly package all this up, we use the phrase significant figures. When we talk about significant figures, we mean all the digits we know for absolutely certain, plus exactly one uncertain digit. Combining those gives us a perfectly honest representation of how much certainty we had during our measurement process. All right, let's look at Tool 3, the rules. Identifying those significant figures. So if you're looking at someone else's data, how do you mathematically identify which figures are significant? Well, to keep track of that certainty, we follow some pretty strict rules. Rule number 1 is super easy. All non-zero digits are always significant. The numbers 1 through 9, they always count. Zeros, however, well, zeros demand a closer look, based purely on where they're sitting in the number. Let's break down a few scenarios. First up, captive zeros. Think of these as zeros squeezed between two real numbers, like the zero smack in the middle of 3090. Because they're locked in by real measurements, they are always significant. But leading zeros, like the ones at the very front of 0.008, those are never significant. They aren't measured values at all. They're literally just placeholders telling you where the decimal point lives. They give us the scale of the number, but no actual certainty. But here's where it gets kind of messy. What happens with trailing zeros when there's no decimal point? Take a measurement like 1,300 grams. Are those zeros just placeholders telling us it's roughly 1,300? Or did a scientist use a super accurate scale and measure exactly 1,300.0? Without a decimal, it's completely ambiguous. We literally don't know. And that ambiguity is exactly why scientists rely so heavily on scientific or exponential notation. Scientific notation completely strips away those confusing placeholder zeros. It leaves only the true significant figures in the front and moves the scale of the number into the exponent. Consequently, using scientific notation guarantees that our final mathematical answers are reported with only the intended uncertain digits, completely preventing anyone from misinterpreting our hard-earned data. Moving to Tool 4, the map, dimensional analysis. Let's transition over to what we call the factor label method. This is essentially your definitive map for navigating really complex mathematical calculations. And the golden rule here? It means that the units of your quantities, things like grams, meters, or seconds, have to go through the exact same mathematical operations as the numbers attached to them. You don't just multiply the numbers, you are literally multiplying, dividing, and canceling those English unit labels right alongside them. Now, the absolute key to reading this map correctly is mastering the conversion factor. In English, a conversion factor is basically just an essential ratio. In other words, it's a fraction where the numerator on top and the denominator on the bottom represent the exact same physical quantity, they're just expressed in different units. A classic example. 2.54 centimeters is the exact same physical length as 1 inch, right? Because the top and bottom of that fraction describe the identical real-world value, mathematically speaking, dividing one by the other is basically just the number 1. When you multiply your data by this ratio, you successfully change the unit label, but because you're effectively just multiplying by 1, you aren't messing up the actual intrinsic value of your measurement. So, in practice, here's how you actually use this map. Step 1. Look at your given units. Step 2. Identify the units you actually want. Step 3. Multiply your given data by that conversion factor, but arrange the fraction so the original units systematically cancel out, top to bottom. If you start with inches on top, you've got to put inches on the bottom of your conversion factor. They cancel each other out perfectly, leaving you exactly your desired destination unit. And finally, Tool 5, the dictionary, our critical vocabulary box. To really solidify our English immersion today, let's just do a quick review of the critical academic language we've picked up. This table synthesizes our core terminology, so take a second to really anchor these words in your mind. We have accuracy, which means closeness to the target or correctness. We've got precision, the reproducibility of your results, or consistency. Sig figs, which are all your certain digits, plus that one uncertain digits. Dimensional analysis, our systematic map for converting units. And finally, the conversion factor, a ratio of equivalent quantities. These specific English terms are basically the bedrock of how scientists communicate data globally. As we wrap up this explainer, I'd love for you to think about how these foundational tools actually shape how we understand information every day. Next time you read a bold statistic in an article, or even just measure out ingredients for dinner, ask yourself, are these numbers actually precise and accurate? Or, much like our friend Archer X, are they just being precisely inaccurate? Are you absolutely certain those measurements hit the bullseye? Thanks so much for joining me today, and remember to always question the certainty of the data around you.